We have observed very strong heat transfer by charge carriers, also known as thermoelectric effects. We started with nanocrystalline silicon microwires with a high doping density. Due to the low resistive nature of the wires, a large electrical current is forced through when the wires are biased with an electrical signal. This leads to a rise in wire temperature and forms a temperature profile due to self-heating, also known as Joule heating. As electrons climb the temperature profile, their total energy composed of chemical potential and kinetic energy, also known as thermoelectric Peltier coefficient, increases. This leads to energy absorption from the lattice. As electrons descend the temperature profile, their energy decreases, hence they release their excess energy to the lattice. This process is part of the thermoelectric phenomenon and called electronic convective heat transfer. More importantly, minority carriers, namely holes for this case, are generated in the hot regions of the wires and drift in the opposite directions of electron flow. As the thermally generated holes are drifted, their Peltier energy increases, leading to energy absorption through the lattice by holes. Once the holes reach the end of the wire at a lower temperature, they recombine and release energy. The latter process, called generation transfer recombination, dominates over the electronic convective heat transport, leading to a skewed temperature profile towards the source of the majority carriers, namely electrons. This process is illustrated on a simplified energy band diagram of a wire. Generation of electron-hole pairs takes place in the hotter region, yielding energy absorption from the lattice. Electrons and holes are then separated and drifted by the electric field, causing Joule heating, which is the main heat source. The excess holes recombine with incoming electrons on the other end of the wire, yielding energy released to the lattice. The total current along the wire is constant and dominated by the electron current at the cooler regions, whereas the hole current is significant at the hotter region. Due to this asymmetric heat generation, the hottest spot shifts to where the minority carriers leave the wire. Once the temperature on the wire reaches the melting temperature of silicon, the wire asymmetrically melts and resolidifies upon termination of the electrical signal. The explanation of asymmetric temperature profiles in terms of significant heat transfer due to minority carrier generation transfer recombination is our key findings in this work. This sheds light on previously reported similar asymmetric self-heating of small-scale structures, such as polysilicon microlamps and phase change memory devices. The asymmetric self-heating of the wires was also observed optically. As the wires emit light due to self-heating, the hottest spot on these p-type wires was observed to be shifted away from the wire center and towards the source of the majority carriers. The asymmetry in light emitted from the wires is more visible when the electrical current direction on the wires is alternated. For this case, the hottest spot location alternates with current direction, proving carrier and heat transport are coupled. Albeit its interesting nature, why should anyone care about this phenomenon? It is because the same phenomenon is expected to be very strong for any self-heated small-scale device, such as phase change memory. Phase change memory is a non-volatile memory technology which has been recently released. The state of the memory is stored by changing electrical resistance of the chalcogenide material in between metal contacts. When the chalcogenide material is in crystalline phase, it is electrically conductive. When a short-duration electrical pulse is applied across this device, a small volume of the chalcogenide material melts. Upon termination of the signal, the material then amorphizes, resulting in a larger electrical resistance. During this melting and amorphization process, the temperature gradient in the device can be as large as 10 Kelvin per nanometer, which leads to strong thermoelectric effects. The initial crystalline state is achieved by self-heating the amorphized volume with a lower amplitude and longer duration electrical signal. With this, we conclude our summary of strong thermoelectric transport observations on self-heated silicon microwires and broader impacts of these observations on phase change memory devices.